Hello, welcome to another lesson on All About AI.
This is the third part of Data Preprocessing tutorial.
We have already seen that data preprocessing is like refinery process that happens for crude oil. So in data preprocessing, raw data is processed through various
Preprocessing steps.
and then that processed data is being used for machine learning and AI algorithms. We have already seen data cleaning, data transformation, data scaling, data encoding, data reduction. Now, in this lesson, we'll be talking about data balancing, data discretization, data integration, data anonymization, data augmentation,
Text preprocessing, image preprocessing, time series preprocessing.
So let's first start with data balancing. So data balancing happens when there is an imbalance in the dataset for the target classes.
Typically, we see dataset with rare events have data imbalance. Like in case of medical dataset on cancer, only a small percentage of people are diagnosed with cancer. Same is fraud data in case of credit card transaction dataset.
Now what happens is this imbalance often leads to bias and algorithm cannot process the minority classes properly. So there are various methods to address this data imbalance. Some of them are oversampling, undersampling, hybrid methods, ensemble methods, algorithm level methods, class weight adjustments.
First, we'll take a look at oversampling method. In this case, we can balance dataset by generating new synthetic data or duplicating existing ones.
Like we'll be sampling multiple times, and often after that, both the classes will have almost similar
Distribution of classes in the dataset with which model will be trained.
So if you see here, SMOTE, which is a well-known process to synthetically generate data. So in this case, original data has imbalance because of majority class is more data compared to the minority class. So what we'll do, we'll be generating synthetic data using some mechanism, and those data will be used in the final algorithm training.
Another method is undersampling.
So in this case, we'll be selecting some sample from majority class, and using that, the algorithm will be trained. So if you go by the similar example, the original data set,
We'll take few samples from majority class.
and for minority class, we'll take it as it is.
After this undersampling, dataset will have balanced data points with which the model will be trained.
The next way to do it is hybrid methods. In hybrid methods, we will increase the minority class, and at the same time, we will also decrease the majority class. We can use SMOTE plus edited nearest neighbor or SMOTE plus domain links. Another way to do it is ensemble method. In this method, we will be using ensemble technique like bagging or boosting to combine with the sampling methods. Algorithm, balanced random forest, easy ensemble, and balance cascade. These are the methods part of ensemble methodology. These are a little bit advanced ensemble techniques where multiple balanced datasets are created using resampling, and the model is trained using these aggregated datasets. There is another way to handle sampling is cost-sensitive learning. So in this cost-sensitive learning, the higher cost is assigned to misclassification of the minority class. By assigning higher cost at the time of training, if it is misclassify the minority class. There is another way is class weight adjustment. So instead of changing the dataset, this approach modifies the learning algorithm such a way that it penalizes misclassification of the minority class more than the majority class. So there is a penalty that works in this case.
Now question is when we should use all these techniques during the pre-processing step to balance the dataset.
So if we see there is a significant class imbalance, then you should use it, particularly if it is a binary classification and if one class is underrepresented, there is a best case to use these methods. Also, when matrices like F1 score, precision, or recall are crucial, then we should use one of these methods to balance the dataset. But do note, there is always a risk of overfitting if we use
Oversampling technique.
some models handle imbalance inherently.
We also need to be careful about data volume as balancing can increase the data size.
And it's important that we should use metrics beyond accuracy if the classes are imbalanced. Next, we'll look into data discretization. Now, in data discretization, the purpose is to transform the continuous data into discrete intervals. So if you see here, there are a lot of data and we can convert them into some discrete interval levels. In certain dataset and certain algorithms cases, it improves the model performance. It also simplifies the models, improve the interpretability. It does noise reduction. Sometimes it handles outliers very efficiently. And it also improves computational efficiency. Now we'll take a look into various discretization methods. One of the very popular one is equal width discretization. It divides the range into equal width intervals. Simple but may result in uneven data distribution. Equal frequency discretization. This is done by creating equal number of data points. This ensures well populated intervals. K means discretization. This uses clustering to create intervals. Decision tree based discretization. This uses algorithms like CART for splitting data optimally. Since this is a supervised method, it can be computationally quite expensive. Next, there are entropy based discretization, which uses information gain to determine boundaries. Effective for classification task. Chi-square based discretization merges interval based on chi-square statistic. Binning by rank. This is also called quantile binning. This creates intervals based on percentiles. This ensures the data is distributed uniformly. There are a few other methods like minimum description length principle, Jenks natural breaks, and there are also few domain specific methods. Now, when to use discretization? If algorithm requires categorical input, sometimes to improve model performance and to reduce noise, and also to increase interpretability, this is often used. But it's important to note, it's not always necessary. Sometimes it leads to information loss. It can have an impact on specific dataset and model while evaluation. Next, we'll take a look at data integration. Data integration is the process of combining data from different sources into a unified dataset to improve analysis and model training in machine learning. It ensures consistency. Sometimes it's enhance data quality. Also, different sources make data more diverse. And also, comprehensive and accuracy can be improved by combining multiple sources. Ultimately, it is for quality, quantity, and diversity that improves the model performance. Now, if we take a look, there are a few ways of doing integration. Some integrations are feature level. So it could be like feature concatenation while combining multiple features from different sources into a single feature vector. Feature fusion, combining features using weighted sums or more complex function. Multi-view learning, training separate models on different feature sets and combining their outputs. There is also model level integration possible, like ensemble methods, where combining predictions from multiple models, like we have seen boosting, bagging, stacking, etc. These are example of model level integration. Transfer learning is another area which is getting very popular nowadays, and this uses knowledge from one domain to another domain. So in this case, it's the learning from one domain is used to improve performance in another one. Another method is called federated learning, where the training done across decentralized devices or servers without exchanging raw data, and later they are combined together. There is also data level integration. Like we know about data warehousing, data lakes, ETL process, where data is aggregated, extracted, transformed, and loaded from various sources. There is also semantic integration, where using ontologies and knowledge graphs to align data from diverse domains.
Now the question is when to use data integration. When data is scattered across different systems or database, then we should use data integration.
Also, if we see incomplete data, to fill the gaps, combining related datasets is useful. In certain complex analysis, we require data from various domains and also from different perspectives. Important note, when using this pre-processing method, we have to ensure that data quality from different sources is consistent. There is a compatibility between different data sources in terms of formats, schemas, data structures. Sometimes scalability is one concern due to time and storage constraint. Privacy and security is paramount in today's world, where protecting sensitive information during the integration process is important to take note of. Next, we'll take a look at data anonymization. Data anonymization is the process of transforming personal or sensitive data so that individuals' privacy is protected while using the data for machine learning models. So if you see in this example, the name of a person is converted into some number and letters combination, which is difficult to find out just looking at that anonymized data. So purpose of data anonymization is to preserve the privacy, enabling valuable data used for training models. Also, sometimes it's due to protection and conforming to the regulations like GDPR, HIPAA, enabling data sharing collaboration in ML projects. It is quite important in sectors like healthcare and finance where sensitive data is prevalent. It allows organizations to leverage large datasets for robust ML without compromising individual privacy rights. Now, there are various ways to do anonymization. Data masking is one of them, which replaces sensitive data with realistic fake data. For example, substituting real name with fictitious name. Pseudonymization, replacing identifiers with pseudonym. This allows re-identification if necessary. Data generalization, here replacing specific values with broader categories. Converting exact age to age ranges. K-anonymity, ensuring each record is indistinguishable from at least K-1 other records. It protects individual identities while allowing more meaningful analysis. Another way is differential privacy, adding statistical noise to data or query. This ensures inclusion and exclusion of a single data point doesn't significantly affect the outcome. Data perturbation. This is the way where a little bit noise is added to numerical data to obscure the individual values. It ensures the overall statistical properties are retained. L diversity, ensuring sensitive attributes have diverse values within each group of anonymous records. Enhances privacy protection against inter-inference attacks. Synthetic data generation, certain areas creating artificial data that mimics the statistical properties of the original dataset. Now, when to use? Mostly it is required to handle sensitive personal information, as we have seen for healthcare, financial data. When data need to be shared with third parties or public dataset, it is also required to complying with privacy regulation, protecting sensitive information in ML research and development. There is always a balance needed between privacy and utility of data. There is no perfect anonymization method. It's always required to reassess. Consider combining multiple techniques for stronger protection. It's recommended to regularly review and update anonymization strategies as machine learning techniques are ever evolving. There is always a potential bias introduced and performance impact due to anonymization. Ongoing assessment of anonymization method is critical as advanced techniques may lead to re-identification. Now, we'll quickly go through remaining 4 categories: data augmentation, text preprocessing, image preprocessing, time series preprocessing. So, for data augmentation, in data augmentation, we artificially expand the size of training dataset by creating modified versions of existing data. Usually, this technique is predominantly used in image, text, and audio. In image augmentation, we use like rotation, flipping, scaling, and adding noise to image. For text augmentation, it's replacing synonym, random insertion, or back translation to generate new text samples. For audio augmentation, we add background noise, time stretching, or pitch shifting. These are the methods used for audio augmentation. Now, what is the benefit of having data augmentation? Reduce overfitting by exposing model to various additional data. It also improves model robustness and accuracy. And especially when there is a limited data, data augmentation helps us to create more data to train the model effectively. This is widely used in computer vision, natural language processing, and speech recognition tasks. Next, we'll look into text preprocessing. So text preprocessing involves transforming raw text into clean and structured format suitable for machine learning models. There are various methods involved, like tokenization, where splitting text into individual words or tokens, lowercasing, converting all characters to lowercase to maintain consistency and uniformity. Stop words will be removed, like and, the, or. Stemming, lemmatization, reducing words to their root form, like running will become run. Vectorization. Many algorithms require converting text into numerical representation, like TF-IDF, word to vector, etc. Text preprocessing enhances the quality of data, and it leads improvement in model performance, is very useful in sentiment analysis, text classification, and many more. In fact, in all chatbots like ChatGPT, Gemini, all are using many sophisticated text preprocessing. Next, we'll take a look at image preprocessing. In image preprocessing, the raw image data is converted into suitable format that machine learning model can understand. This step is crucial to improve model accuracy and performance. Key techniques are rescaling, where we adjust the pixel values, typically normalized within a range. Resizing, alter the dimension of image to ensure consistent input for the model. Data augmentation, as we have seen already, that various techniques for augmenting data is being used for image. Denoising, remove noise from image using filters like Gaussian or median. Histogram equalization improves contrast by redistributing the intensity value of the image. Now, preprocessing for image ensures the optimal format for training, leading to better model performance and generalization. Next, we will look at time series preprocessing. In time series preprocessing, which is a little bit unique compared to all other processing, there are different things being done to ensure data is processed correctly. And lag feature engineering create lag feature to capture temporal relationship with previous timestamp. Differencing. Apply differencing to remove trends and make the series stationary. So differencing ensure there is no relationship between two data points. Rolling window calculations use rolling windows to compute moving averages, standard deviation, etc. for smoothing and pattern detection. Seasonal decomposition. Decompose the series into trend, seasonal, and residual components to isolate patterns. Resampling. Adjust the frequency of data points, like from minutes to hours or seconds to minutes, to match the analysis needs. Also, there are various time zones being used, so it's important to normalize those time zone specific data into a standard time zone to ensure consistency. Now, with that, we come to an end of our data pre-processing lesson. So we have covered in this lesson data balancing, data discretization, data integration, data anonymization, data augmentation, text pre-processing, image pre-processing, time series pre-processing. So with that, our data pre-processing, which is chapter 2, completes. We'll move into chapter 3 in next lesson. Thank you so much.